Hello everyone, this talk is on best fit bin packing with random order. My name is Leon Ladewig and this is joint work with Susanne Albers and Agendam Khan.
Let me start by presenting the problem. So in the bin packing problem, a list of items is given. Each item has a size between 0 and 1, and the goal is to find a packing of these items into the minimum number of bins of size 1. So a packing of these items could look like this. And we study the online variant of the problem, which means that the items arrive one by one, and an online algorithm needs to pack the current item without knowledge of the future items. Two quite simple algorithms for bin packing are NextFit and BestFit, and in particular both of these algorithms are online algorithms. That's why I will present these algorithms here. I will start with NextFit. The policy of NextFit is to pack items into the current bin as long as they fit there. As soon as there is some item which does not fit into the current bin, a new bin is opened for this item and the previous bin is considered as closed. So no item can be packed there. And this leads to the following packing using 5 bins in this example. The best fit algorithm is in general better than next fit. So the policy of best fit is to pack the current item into the fullest bin where it fits. Otherwise, again, a new bin is opened for this item. So in this example, actually the packing for the first few items is identical with next fit. Then on arrival of this light blue item here, we see that there are 2 bins where this item fits, namely the first bin and the second bin. However, the first bin is the fuller bin of these 2, so best fit will pack the light blue item into the first bin. And finally, for the orange item, again a new bin is opened. So we see that best fit uses only 4 bins here, while next fit needs 5 bins in this example. To analyze the performance of an online algorithm, of course, we want to compare the number of bins used by the online algorithm with the number of bins in the optimal packing. However, different metrics and models exist. So one very common approach for online algorithms is the so-called adversarial model, where we assume that an adversary chooses the instance, which means the item sizes here, as well as the order of items. In this model, we can use the notions of absolute ratio and asymptotic ratio known from approximation algorithms. So the absolute ratio of an algorithm is just the worst case ratio between number of bins of the online algorithm and opt_i, the number of bins in an optimal packing of instance I. In the asymptotic ratio, we consider basically the same term, ai divided by opt_i, but we assume that opt_i goes to infinity. Sometimes the adversarial model is too pessimistic. Note that the adversary is really powerful here because he chooses both the instance and the order of items. And the idea of the random order model, which was proposed by Kenyon, is to weaken the adversary in the following way. The adversary still chooses the instance, but the order of items is drawn uniformly at random. And again, we obtain 2 notions of approximation ratio, absolute random order ratio and asymptotic random order ratio. We have basically the same terms as in the adversarial model. The only difference is that the number of bins which is used by the online algorithm now is an expectation over the random permutation. Let me come to previous work. The 2 algorithms, BestFit and NextFit, which I presented a few slides ago, are of course well studied in the adversarial model. So here we know that for BestFit, the absolute and the asymptotic ratios both are 1.7. For NextFit, we know that both of these terms are 2. These are results for the adversarial model. However, more relevant for our work are results in the random order model. So actually Canyon introduced this model in 1996 and proved for best fit that the asymptotic random order ratio of best fit is between 1.5 and 1.08. So Canyon showed some upper and some lower bound on the asymptotic random order ratio. So in particular, the upper bound of 1.5 shows that random order is able to break the upper bound of 1.7 in the adversarial model for best fit. Interestingly, it has been shown later that the next fit algorithm does not improve under random order. So still in the random order model, the asymptotic ratio of next fit is exactly 2. So we see that the next fit algorithm has been studied in the random order model and there's nothing more to show. For best fit, of course, we see that there's a gap between 1.5 and 1.08, which can be improved, and we make progress in this open problem. Of course, there are also many other problems studied in the random order model. Problems which are most related to our work are from bin covering, matching, and scheduling. Okay, let me come to our results. Our first result is an improved upper bound for large items. So we show that for any list of items which are larger than 1/3, the random order ratio of best fit is basically 5 divided by 4. Our second main result is an improved lower bound for the asymptotic random order ratio. We show that this term is larger than 1.1, and by this we improve upon the 1.08, which was previously the best known lower bound for the problem. In the remaining time, I will talk about these two main results. Further results in the paper include bounds on the absolute random order ratio, and we study the monotonicity of best fit in case of large items, and we will see some part of these monotonicity properties in the next part. Okay, in this part of the talk I will explain the upper bound for large items. So we assume that all items have sizes larger than 1/3 here. This means that we can define two item types. We say that an item is large if its size is more than 1/2, and we say that an item is a medium item if it is larger than 1/3, but at most 1/2. And this implies that in the optimal packing of such an instance, we can have 4 different configurations of bins. So each bin can contain either a single item, L or M, or a combination of L and M, or M and M. And accordingly, we call these types of bins L bin, M bin, LM bin, and MM bin. We further define the notion of LM pairs, which are just pairs of L and M items which are packed into the same bin in an optimal packing. On a high level, the upper bound for large items is in 3 steps. In the first step, we can show that it is without loss of generality to assume that we have an instance which consists of LM pairs only. So actually we assume that the optimal packing does not have 4 different configurations, but consists only of LM pairs, which makes it easier to analyze, of course. The second step in the proof, maybe the main ingredient for the whole proof, is the notion of good LM pairs. So these are LM pairs which have some nice properties. And as a consequence, we can show that good LM pairs have some positive implications on the packing. Let me start with the first step, the reduction to LM pairs. Here we use the notion of monotone algorithms. We call a bin packing algorithm A monotone if the number of bins can only increase if we increase the sizes of items. This really sounds like a natural property of an algorithm, In fact, this is true for the next fit algorithm, for example. However, the best fit algorithm, which we consider, is not monotone in general. There are counterexamples for this, and we also present some easy counterexample in the paper. However, we were able to show that if each item has size more than 1/3, best fit is monotone, in fact. And this helps in the following way. So still we want to reduce the number of configurations in an optimal packing in a way that we make the problem only harder for best fit. And we can use monotonicity here as follows. So starting from these 4 different configurations which might occur in the packing, we use the monotonicity property to increase the sizes of the items. In case of the bins which contain only 1 item, we increase this item, and for the bins containing 2 items, we just choose one of them and increase it such that the total size of the items in the bin is exactly 1. Okay, and by this step we obtain an instance where each bin is either an L bin, where the L item has size 1, or it is an LM bin containing 1 L and 1 M item. So the last step is to argue that we can discard the L items, but this is easy to see. So in the end, we obtain an instance of LM pairs only, and this is a nice structure to analyze. So from now on, we assume that I denotes a list of k LM pairs, and this implies that also the number of bins in the optimal packing is k, because this packing contains k LM bins. Now we come to the concept of good LM pairs. For this purpose, we consider a small example of 4 LM pairs, and we consider 2 permutations for such an instance. In the first permutation, all L items arrive within the first 4 rounds, and the M items arrive in the later rounds. So for any LM pair, we have the property that the L item arrives before the M item. And for such a permutation, it is easy to see that best fit opens new bins for each L item, but then on arrival of each M item, this M item can be packed into the corresponding bin. So best fit opens exactly k bins here, which means best fit is optimal. On the other hand, consider the case where all M items appear in the first half of the sequence and all L items appear in the second part of the sequence. This is the worst case scenario of best fit if all items are larger than 1/3, because all M items are paired in groups of 2 and packed into the same bin, which opens k divided by 2 bins, but then on arrival of each L item, this item cannot be packed into some existing bin, so best fit opens k additional bins for the second part of the instance, which means best fit uses 3x2 k bins here. So these 2 extreme cases motivate the notion of good LM pairs. We say that an LM pair Li-Mi is a good LM pair if Li arrives before Mi in the considered permutation. Note that in the permutation shown on the left, all LM pairs are good, while in the permutation on the right, we have no good LM pairs. So these are the 2 extreme cases which can happen. Actually, we deal with permutations drawn uniformly at random, so maybe we would expect some permutation like this, which has 2 good LM pairs. Also, the good news is that in a random permutation, we expect k divided by 2 LM pairs. So 50% of all LM pairs are good in a random permutation, which is due to the fact that for each LM pair, the probability is 1/2 that Li arrives before Mi if the permutation is drawn uniformly at random. Okay, finally we come to the implications of good LM pairs, and here the main lemma is as follows, The number of good LM pairs in the permutation is of course a random variable which we call x here, and the claim is that if we have x good LM pairs, then the packing of best fit has at least x LM bins. And intuitively this is good because many LM bins mean that many L items get matched to an M item, which implies that there's only a small number of bins which contain only a single item. Okay, so I will sketch the proof in the following. We denote the x good LM pairs by L1 M1 till LX MX, and we assume that the M items are numbered by order of arrival. So M1 is the M item which arrived first, and so on. The claim from the lemma can be shown inductively. So the induction hypothesis here is that on arrival of Mi, the best fit packing has at least I LM bins. So we can assume this hypothesis, and now we need to show the claim for I plus 1. And for this purpose, we consider the packing on arrival of Mi plus 1. As we know that Mi plus 1 and Li plus 1 is a good LM pair, we in particular know that Li plus 1 already arrived. So there is one bin which contains the item Li plus 1. And we consider two cases here. The first case is Li plus 1 is available. By available, we mean here that there's no other M item packed into the bin of Li plus 1. If this is the case, the online item Mi plus 1 either gets packed into the same bin as Li plus 1, which gives a new LM bin, or it could also happen that there is some other item Lj, which is larger than Li plus 1, but still Lj and Mi plus 1 fit together in one bin. And then best fit would pack the M item with Lj. This might happen, but this is also fine because also in this case we get a new LM bin. So in both cases, after packing Mi plus 1, we have I plus 1 LM bins, or at least I plus 1 LM bins in the packing. Finally, we need to deal with the case where Li plus 1 is already packed with some other M item. Here again, two cases can happen. Either best fit packs the Mi plus 1 item with some L item. In this case, we are also happy because we obtain some new LM bin in the packing. If this is not the case, so Mi plus 1 goes into a new bin, then we can show that in this case we already have at least I plus 1 LM bins. Actually, this argument is a bit technical, that's why I'm not going into details here. But yeah, in case 2, we again have these two situations which can occur. And in both situations, we get that the number of LM bins in the packing is at least I plus 1. And this concludes the proof of the lemma. And finally, we just need to analyze what happens now. So if we assume that we have a number x of LM bins in the packing, what is the approximation ratio of best fit? So how many bins are used by best fit compared to opt? Okay, if we have x LM bins in the best fit packing, the worst case is that all remaining M items are packed in groups of 2 and all remaining L items are packed into single bins. By adding up these terms, we get that best fit uses at most 3 by 2 k minus x divided by 2 plus 1 bins. And if we plug in that the expectation of x is k divided by 2, we obtain the 5 by 4 bound here. And this concludes the proof of the upper bound for the case where all items are larger than 1/3. Okay, in the remaining minutes I will briefly sketch the construction for the lower bound. This approach is based on the connection between the i.i.d. model and the random order model. So the i.i.d. model is some other model from probabilistic analysis. Here, the item sizes are drawn independently and identically distributed according to some discrete distribution f. So in contrast to the random order model, the i.i.d. model is drawing with replacement. The random order model is drawing without replacement. The performance measure in the i.i.d. model is again the ratio between the algorithmic and the optimal solution. However, here both terms are in expectation because the sequence of items itself is a sequence of random variables. In general, one can show that the i.i.d. model is weaker than the random order model, which implies that lower bounds for the i.i.d. model hold also for the random order model. This was observed earlier in the literature, and we follow this approach, which means that we construct such a distribution where the performance measure for the i.i.d. model gives more than 1.1, and by this approach we obtain some lower bound on the asymptotic random order ratio. The discrete probability distribution is quite simple in our case. The distribution gives only two different item types, either one item of size 1/3 with probability p, or an item of size 1/4 with probability q, which is 1 minus p. For such a distribution, it is not hard to analyze the optimal algorithm in expectation. The optimal algorithm will group these items according to their type, which means we can just use the expected number of 1/3 items, divide this term by 3, and accordingly for the other item type, and get the expected number of bins in the optimal packing. To analyze best fit on this random instance, it is actually enough to consider the open bins of best fit at any time of the packing. Here, open bins are those of remaining capacity at least 1/4. Such bins can receive items in the future. On the other hand, bins of remaining capacity smaller than 1/4 can be considered as closed because no item can be packed there in the future. Okay, and the first observation is that the best fit algorithm for this configuration of item types maintains at most 2 open bins at any time. So we can model the behavior of best fit by the following Markov chain. In the initial state, of course, we have no open bin, and then depending on which item arrives, we are either in state B or in state C. From states B and C, of course, we can reach new states according to the next item, but in total we have only 9 different states, A to I, in this Markov chain. Recall that we want to analyze the number of bins which are opened by best fit, and if we consider the state diagram more carefully, we know that this happens on the transitions from A to B, A to C, and G to H. So we can express the number of bins opened by the best fit algorithm in terms of the number of visits to some certain states. So formally we define Vs of t to be the number of visits to state S up to time t, and then we can express the number of bins used by best fit by this term, depending on the number of visits of states A and G. Now we can conclude the proof by using some result for ergodic Markov chains. The Markov chain which we consider is ergodic in fact, and so the following holds. The term 1 by t times Vs of t converges to omega s, where omega is the unique stationary distribution of the Markov chain. Using this result and setting p, the probability of a 1/3 item, to 0.6, we can plug in all these results and obtain that this distribution gives an i.i.d. performance measure of larger than 1.1, which implies that the asymptotic random order ratio of best fit is larger than 1.1. This concludes my talk, so thank you very much for watching this video.